עכשיו עובד? Oh, okay. Again. Okay, so welcome one and all to COCO 2018. We'll start by asking Professor Nachum Shimkin, the Dean of our Electrical Engineering Department, to say a few words. Nachum.
Yeah, I'll be careful. I think this is recorded, so we must speak to the microphone. So I'm very pleased to host this meeting at the Technion and in our department in particular, in electrical engineering here. I'm sure that everyone here is aware of the prominent role that this department played over the years in the science of communication information theory. Starting with the contributions of Jacob Ziv, Israel Bar David, Abraham Lempel, and the late Moshe Zakai, and many others who follow, some of which are here. So this is part of the German-Israeli project cooperation, and indeed in the name of the workshop, we have Workshop of Coding, Cooperation, and Security, so I'm sure this is symbolic of this cooperation. I would like to congratulate the organizers, Gerhard, Chaim, and Ido, who are sitting here, for all they have done for making this a success. I'm sure Ido will elaborate on more people who were part of that, and for putting together an impressive program. And I wish everyone an interesting and enjoyable meeting, of course. Let me elaborate a little bit about the cooperation with this German-Israeli project. So this is supported by the German Research Foundation, DFG, and the German Federal Ministry of Education and Research. And the workshop is also sponsored by the Ollendorf Minerva Center. This center was founded in our department as one of the first Minerva Foundation Centers established in Israel by the German Ministry of Science with the goal of promoting cooperation with German universities and research institutes, and I'm very glad to see this cooperation persisting and continuing. Let me, in closing, share some happy and good news. And the good news is that the winners of the 5th annual Nokia Bell Labs Prize for Shaping the Future of Information Communication Technology were announced on Wednesday, December 5, last week. And the third place prize was awarded to two of the people who are here today. This is Benjamin Zeidel, Benny, from Bar Ilan University, and Shlomo Shammai from the Technion, who will be the next speaker. So this is a wonderful achievement, and congratulations to Shlomo and to Benny. And the prize is for sparse communication, closing the gap to the ultimate performance limit. I understand it is related to NOMA. Everyone here knows what NOMA is. So congratulations again. Well done. So with this, I will wish you a very enjoyable workshop and have a good scientific program. Thank you.
So hello from my side. I'm Gerhard Kramer from the Technical University of Munich. A few words were already said about the funders, but I wanted to just briefly say how this workshop came about not too long, and also mention one other funder who's on the list. So as was mentioned, the original motivation was that together with Chaim and Moshe Schwartz and Antonia Wachtatze, who's assistant professor in Munich, she did her postdoc together with Tuvi Etzion, and also Eitan Jacobi, who's over there. So there's a lot of connections between Munich as well as Technion in this respect too. So there's 4 people involved in this. In Germany it's called DIP, Deutsch-Israelisches Projektpartnerschaft. And I think you call it GIFs for German-Israeli, I don't know what the F stands for. But it's a very nice type of project that I would also encourage people here to consider because it's well funded and it runs over 5 years, so it allows for long-term cooperation. So when I was visiting here through that in March and in May, that's where I got to talk with Ido about potentially organizing a workshop, and I would like to congratulate him too. I heard he just got approved for tenure. It wasn't? Oh, I thought, okay, it will be then. Someone told me that this morning, but perhaps he was a little bit too optimistic at this stage in time. So anyway, I'm sure that will work out soon. As often happens when you first discuss potential work and events like this, it sounds good at first until it gets serious. So it took some time to actually make the final decision, which we did do, I think, at the beginning of November, so it was actually not so long ago. And I'm glad that it worked out now. And Ido will say a few thank you words in just a moment. I want to add one more funding agency that is involved. So it's not just the DFG and BMBF, so the Ministry of Education and Research in Germany, not just the Minerva Foundation, but also something called the International Graduate School of Science and Engineering in Munich. And that plays a special role because Technion will join the Eurotech Universities Alliance starting in January. So this is an alliance of European universities, including the Technical University of Munich, EPFL in Switzerland, the Danish Technical University, École Polytechnique in Paris-Saclay, that just joined in the summer, and Technion, that agreed to join starting in January. The purpose of this alliance is to have a consortium that motivates larger scale funding from the European Union, the European Commission. I'm quite sure other alliances forming too. And the International Graduate School for Science and Engineering at TUM is deliberately a interdisciplinary institution that gives out money funded by the German Research Foundation, and next year there will be a special call for Eurotech partners. So there's also an opportunity to start up projects there. So I just wanted to briefly mention that. Okay, with that I will stop and let Ido say thank you for the organizational work as well.
Okay. Okay, so thank you, Gerhard. First of all, thank you all for coming, and it looks like it's going to be a very interesting program. I'm looking forward. I'm sure you are too. Thanks. So first of all, in terms of funding, thank you very much to the Ollendorf Minerva Center for Vision and Image Sciences, and particularly Professor Giuseppe, and also to the Hiroshi Fujiwara Cybersecurity Research Center, and particularly Ms. Suzy Eid, Hila Mizrahi, and Professor Eli Biham. Thank you once again to the E department for hosting us, and for Professor Nachum Schinkin in particular. And also thank you very much to Yoram Olchen, who is not currently filming, but will be filming. And a special request from him, you need to use the microphone at all times, so it's recorded. And also, if there's a question from the audience, please repeat it, so it's recorded as well. Also, my co-chairs, thank you again, Gerhard and Chaim. Thomas Wiegert, who was in charge. I saw him. Where is he? Ah, here you are. Yes. Thomas was in charge of the webpage, and we would nag him constantly to update it, so thank you once again. And at last, a very big thank you to Iris Berg, who more or less single-handedly organized this conference. I really think she's in the right place, and I'll explain, because she is a very good error corrector. And those of you who know me have by now figured out who the noisy channel is. But nonetheless, things seem to be working. Okay, I think that's it. Let me just check because otherwise I'm in trouble. Yes, I think that's it. Okay, so now it's time to introduce our keynote speaker, Professor Shlomo Shammai. So I've asked him how should I introduce him, and he said, well, just say that I'm Professor Shlomo Shammai, actually distinguished Professor Shlomo Shammai, and I joined the E department in 1986. Okay, that's very true, but I think I will elaborate a bit more. But I really have to strike a balance, right? Because I looked at his webpage a few days ago, and I think I counted 36 prizes. And now we've been told that that count has been incremented, so I should speak fast to stay relevant. Okay, so I'm not going to list all of the 37 prizes, but maybe just the important ones, which I think are important. The Hamming Prize, the Shannon Award, twice winning the Joint IT Communications Society Best Paper Award, and also winning the IT Society Best Paper Award. I will leave you to extrapolate from there. Shlomo, please come and give your keynote.
Okay, fine. First, I would like to thank really the organizers, Gerhard, my old friend from Bell Times, and Ido, and everybody else that Ido just mentioned. And thank you, Ido, for the introduction. And thank you for telling me what's on my website, which I didn't open for the last 25 years. Thank you, Gita, for putting everything there. And so let us start, and with your permission, because of the diverse audience, this time I'll skip many technical details. I'll try to give more or less a general picture. So what I would like to speak today is cloud radio access networks with the focus on what is known as distributed information bottleneck, and then look from the information theory perspective, and then hopefully the second part connect that to various bottleneck problems which are now used not necessarily in what we do, mainly communication, transmission of information, but as we well know, machine learning, deep learning, and even other domains like biology. And the results here are based on several works with Inaki Stella Aughieri, Abdelatif Zaidi, and Giuseppe Caire, which is here with us. So whatever we will do, first an introduction, and then look at the uplink cloud radio access network with oblivious processing, that I'll try to describe what it is, and see that in this setting we actually can determine the capacity, which is usually rare for networks, and say a word about the price of this obliviousness, quote unquote. And then the second part, as we say, connection to bottleneck problems and what comes out of them, not just bottleneck. Conclude and mainly outlook where to go, where I think we should go. Okay, this cloud radio access network, a big word today because of 5G technologies. What does it mean? Today, here, 4G, even the beginning of 5G, what do we have with the cellular system? Each user is connected to its own cell, and who decodes the message and then directs it to wherever sent. And that's a big problem. Why? It was very nice, first generation, second generation, so on. Now the systems are so dense because of the crazy rate demands, reliable rate demands, that whenever I am connected to this cell site, and Nahum is connected to another cell site in the same ceiling. So I interfere with him interferes with me, and it's not, even if we say, okay, interfere, what do you mean? Do joint detection, remove the interference? Even that is impossible, because I usually am received with way less SNR at his cell site and the other way around. So this limits, in a way, the possible performance. Why? There's no point to increase power because the interference will increase, it will flatten down. So the idea was, okay, change the network. Make the cell sites dumb, quote unquote, idiotic. Do nothing. Just be connected via links. The links could be optical, internet, whatever, telephone, whatever you want, to a central unit, and the central unit should decode everything. No interference. He belongs, me, and so on and so forth. So that's the idea of the cloud radio access network, where now I discussed only the uplink, and there are many types of cells, macro, pico, femto, whatever you wish. So that's the idea, and this is the thinking for the next generation, and led by quite a number of industries. Huawei to start with. Okay, let us not discuss any more about that. Just look at the model we are dealing with. There are many users connected through a channel to those cell sites, which are now more or less relays. They don't decode. They just try to convey whatever they receive to this, the final decoder at the cloud. And this decoder has to decode all users. There is no association with the specific cell. Decode in a reliable way, the way we are used to. So very easy to draw this picture, very difficult to solve from an information theoretic point of view. The problem is open even for very simple special cases, like the parallel Gaussian relay channel, due to Shane and Gallagher, and many, really hardly countable number of open problems. Okay, and what was the reason that this is that difficult without going too much into details? We can use too many things which are not enough, like decode and forward with the references here, compute and forward with the references here, including our friend Giuseppe here, compress and forward, and whatever I'll mention, noisy network coding, though I didn't say a thing about network coding. It seems absolutely related. Let's see that it is. And now the relay operation could be divided into two different approaches. One, what we call is non-oblivious. Relay is aware of everything. Code books, whatever you want. Strategies, whatever you want. Time, resource sharing. And the other, oblivious or nomadic. The word was first coined in this work with Sanderovich, also with Yossi here, and our friend Gerhard, also here. Dan Sanderovich at the time was my student. He said he'll come. Not yet. No. Okay. So, and this oblivious processing, we'll see how we formulate it, is motivated very much by the practical constraint. What does it mean, oblivious processing? You buy a cell site in the store, put it in your ceiling. It has to know nothing. Has not to know code strategies, actually setups. it works in a kind of non-smart way, we'll see. And how do we model that from an information theoretic point of view? And that has been done by Sanderovich et al. And appears also in the Lapidot-Narayan tutorial. Actually, we say that the codes used by the users, the code books, are totally random and are changed, replaced in a random way per message, so you cannot, there's no ability to learn them. Once you have this, there are too many variables. If it's used just for message, that's it. That makes the problem much, much easier, and with the oblivious idea underlying it. So, what is the picture? The code books, Fs, are known, of course, to the transmitting user, are known, of course, at the central unit that decodes everything, are not available to the relays, and change per user, at each user. It's not that I say work this way, but for the results we need it. And now we'll look under this oblivious constraint, what do we have, what can we say? And whatever we demand is given the transmitted signals, the X, the Y's are independent. That means that noises, or not necessarily Gaussian models, but that the random effects are independent given all the inputs. This is, looks like a natural constraint, but it limits us a lot. Because look in the practical system, some cell sites, some are interfered by the very same transmitter. Say somebody drills here. It interferes, the very same signal interferes with many cell sites, which does not satisfy this. Okay, without this, so once we have the capacity, we also show what is the result if we assume that X are Gaussian, special case. And then many things could be solved out, but Gaussian inputs are not optimal. Let me say at this point already, we'll see. And if we remove this, then we have only bounds, outer and inner. They do not match. So this is the result. This indeed the capacity region itself. As I said, I won't detail too much under this constraint. If you look at the result, of course, you have auxiliaries which are built in a specific way. Remember, the cell site under the oblivious approach should actually do some kind of compression, cannot use the idea that messages are transmitted, oblivious. So this is indeed the full capacity region, and we can, there is a resource sharing or time sharing, if you want, for special cases, parameter Q, and that is essential. Unlike, you know, in a general that we have it, in a specific cases like Gaussian channel, it's not needed. It will be needed here. And we can also bound its cardinality. That's a better bound than the usual bound. Okay, so for that, under the oblivious constraint, we can characterize the capacity. The direct part, I said no details. The direct part is indeed compress and forward with the one difference. Joint decompression of the coding. You cannot separate the operation. It's not point-to-point. We're separating channel coding and the source coding is still optimal à la Shannon. No. Not only not separate that, we cannot separate to do total decompression of all signals and then the coding. This costs us in this model. And we will see that sometimes it doesn't cost us much. And if one looks at this expression, suddenly, oh, it's very reminiscent. This is what we have in noisy network coding. This is what we have in noisy network coding. The problem has nothing to do with network coding. I described it. Still, it's the same expression. Of course, when we came with the special case of it here in Sanderovich, we didn't use this term. This term appeared years later, here, Limetal in 2011. But this is noisy network coding. Here you have the interesting links between two different aspects, two different, majorly different problems that actually are the same. So we said what's going on with compress and forward, we separate the compression and the coding. Meaning first with the code, we decompress the indices, the compression, and then do join the coding of all users. We'll see what does it cost. Converse part, we'll skip all, but mention that the idea is similar to what has been considered by Courtade-Wassman, which is multi-terminal source coding with log loss, not MMSE loss or the loss that we like, that we are used to. Maybe I should be more careful, but log loss. And here, without detailing, at some point we need this. This is a must for us to have the sense, to have converse and achievable matched with all the consequences of optimal operation where indeed this is not satisfied. Oh, some remarks. If you look, say, just on the sum rate to make things simple, this is the sum rate from that equation. Now, we can show that sum rate is achieved, the sum rate, not the origin, also by separate decompression decoding. And actually with a much simpler scheme, sequential Wiener-Sieve. Sequential Wiener-Sieve is what? You decompress what? Wiener-Sieve, you decompress the first relay. Okay. Now it serves as site information to the second one. Both of them site information to the third one. Sequential Wiener-Sieve, when you optimize the sequence. So for both of them, you can achieve the sum rate. Here it is. And the theorem under this constraint, join decompression decoding, separate decompression decoding, sequential Wiener-Sieve. First, let us see, okay. Say I don't use this and do not optimize for sum rates to have this modular function effect. And so how much can I gain with this joint decompression decoding? Here is a simple system, scheme of three, Wiener-based scheme of three elements we'll see. We see joint decompression decoding actually gives something not trivial, even for that simple, very simple system, which was quite surprising. This is the upper bound. What is the upper bound? Quite trivial. Cutset bound. Cutset bound means, or we take C infinity, the front hole capacities, meaning what? We have the central receiver that receives all the antennas of the relays of the cell sites are given to the central receiver free. That's what it means. Or we put the Cutset before that, then you cannot, you put Cutset after the relay, you cannot beat C per relay. This is the connecting line. So this is the Cutset bound, which is not that great between us, the outer bound. Okay, so let's go, that's in general. Let's go for the Gaussian model, which is the characterizing model for this kind of thing. Here we have the relay, K relay, all are multiple antenna, relays, user, whatever, are the standard, are described by the standard expression where the transmitters are subjected to some covariance constraint. Also users are multiple antennas. So, and we have this, meaning all noises, all additive noises are independent. Okay, the theorem breaks, of course, for the Gaussian regime, given that X is also Gaussian, to very simple expression, log determinant order. Here are they. And the optimization, again, under the covariance constraint. Here is Amichai. Amichai came, mentioned him. So, and the covariance constraint, we see it is satisfied on average, meaning that we really need this time sharing, resource sharing, the sharing parameter Q. We really need that, which is, unless C is infinity, that we know, it's not needed. Why can we solve easily for the Gaussian? Also, the auxiliaries are Gaussian, not that big a surprise. And indeed, showing that mainly relies on De Bruijn inequality, exactly as used by Palomar-Verdun. Let's see this, as we said, time sharing. Let's look at a very, very special case, really special case. One user, two cells, two relays. Here we have two Gaussian scalar, non-multiple antenna channels. All relays are connected by C. And what do we have? Here we have a user that transmits at power P. This is the red line. This is the Cutset bound. What is the Cutset bound? Again, the same thing. Either we put the cut here, which you cannot beat C per relay. Either we put the cut here, which means that for this model, you cannot do better than half log 1 plus the sum of SNRs, one user. So this is the first thing, this is the C that flattens out as a function. And here we have the sharing, meaning alpha % of the time we transmit power P over P divided by alpha, the rest quiet. Usually it's useless. In the standard. With finite C, it's important, as we see. Of course, when C gets large, no need. Okay? Now, if you force me, say, no, I don't want it. It's too much. Under latency constraint, what is once per year you transmit million times the power, that's not good. If you force the input to be constant, then there is no point to do anything at the relay sharing, and that can be shown. No point. If the input does not use Q, no need to use it anywhere else. And this is what I said, referring to the high SNR regime, which at the high SNR regime, again, also this sharing is not needed. Resource sharing is not needed. Here we have the region which enables resource sharing. Here, no sharing. And we see if this rate vector belongs to the region with sharing, the same one with small differences that go to 0 belongs to the region without sharing. So larger SNR, the gains to resource sharing become limited and go to 0. So let us take an example for that, and this is how else. The classical circular Wiener model, Wiener cellular model, 3 users. Each user is received with power 1 at its own cell site, with power, with the reduction, with amplitude alpha, which is smaller than 1, at the other 2 cell sites. This is the description of the received signal at the gate cell site, plus Gaussian noise. And all radio units are symmetric, same capacity, same front hole capacity. What do we have here? Here is the model. Single cell processing. This is the system today. Today, iPhone 10, everything, this is still the system. Here, as we said, flattens out, no good. Because what? You increase the power of the users, also the inference increases the same way, so it flattens out. Here we have the simple point-to-point compression. Say, okay, join the compression. Come on, how much do you lose? Just do simple compression at here and transmit there, and just standard point-to-point source coding. What's the big deal? Here we have it. This is joint decompression decoding, so don't undervalue complexity. The gain is significant even for this very, how shall I say, I wouldn't say trivial, but very simple model, too simple model, of course. If for that there is a gain, for the real thing will be much more. And here we have successive Wiener Zev without anything, no time change, no thought. So without playing with that, it doesn't achieve the sum rate as it should if you play with the parameters. And this again, the Cutset upper bound, where here is the Wiener result, they are on Wiener result, meaning that you put all C infinity, so the receiver has all 3 antennas. That's the Wiener result. Now one can say, look, with all respect you say oblivious, nomadic, you came up with the capacity region, as we said. The first work was simple case was with Sanderovich here. But maybe the price is too much. So, okay, make things more complex, okay? If you can gain, with all respect due, simplicity is not the end of the line. So let's check this. So what do we have here? All the previous curves that we did. And here we have a non-oblivious scheme, which is based on compute and forward, thanks to Hong and Kyre. And what is that? What is that scheme? Look, quite sophisticated scheme. Let's go back to the model. All users, all relays, use actually linear lattice codes. What is the advantage of lattice code? We know some integer with integer coefficients of code words is again a code word. Linear. So there is no chance, even in the dreams, that this one can decode all users, all 3 users, because then you lose a lot. But what does this one get? A combination of all 3. So maybe if it decodes a code word, which is a combination, then it's fine. Why? It transmits this code word here. This will transmit the code word it decoded, and so on. Here at the cloud center, we'll have enough equations to decode all users. What's the problem? The channel does not necessarily guarantee us integer coefficients or even if we multiply or whatever we want. The challenge is a challenge. Could be a rational number, alpha. Doesn't have to be rational, because rational is good enough. Then there is a penalty. And that's the integer penalty which appears there. Okay, let's look at the scheme with the penalty, with the everything. So what we have is this. We see at low SNR, forget about that, because the noise kills everything. It's really the worst. But quite fast it goes to what? To the Cutset bound, not less. So one could say, look, with all respect you to obliviousness, forget about that. Very nice that you have a capacity result. From the practical point of view, is it true? No. Why not? Here we see the curve. What do you say? Why not? Why not? Because if we are interested, what all shout here, high rates, high rates, high rates. With high rates, you cannot keep C fixed. Even not by optical channel. Optical channel was 10 gigabits, not that big a deal. Also, the C should scale. If you want the thing to scale with SNR, better also the backhole scales with SNR. And indeed, if we look at this case, where the backhole scales with SNR as well, then we are interested in what is known DOF, degrees of freedom. In degrees of freedom, the compute and forward is not that good. The non-oblivious, here it is. The schemes, whatever, join decompression, decoding, successive ion zip, as you see, you cannot beat them. Degrees of freedom, they are on the Cutset bound. So, okay, so what does it say? Obliviousness really doesn't cost you. And it is so appealing from the practical point of view that I think there is a message here. Okay. Again, here is again that theorem. And if I remove this constraint, that all received signals Y are independent given the X's, this is not capacity anymore. The inner and outer bound look exactly the same, but the probability set over which they are evaluated are different. And this problem is very challenging. Not that much chances to solve it, because a very special case is the Corner-Marto modulo sum problem, which is still open. Okay, so look what we did. And now we go to the second part. What did we do? Let us look again back to a single relay, just to make things simple. We had the source, a relay that transmits the information to this cloud U. So, and how do we measure under oblivious constraint? We measured the quality of information, the mutual information from here to here. And from here to here, we had this constraint C, the backhaul, what we call it. But that's exactly, under the oblivious assumption, this is exactly the classical bottleneck problem, the special case of that, which was, the name bottleneck was introduced by Tishby, not here, in 1999. Just another work by them. So, and for that problem, as we see, as in source coding, U is not necessarily a deterministic function of Y. There is a channel, exactly like source coding, from Y to U. Let's use their terminology. So X are what is called features. Y, the observation. We have an encoder that operates at rate R, Y not C, because they use the word R. And a decoder that tries to estimate this x, the features. And they have this. This is the u. Whatever we call front hole, they call complexity. And whatever we call the rate, they call relevance. So the problem is either maximize relevance under given complexity or minimize complexity under given relevance, same thing, the way you look. This is the bottleneck problem, which is same thing, but with a very simple case. It's very nice that this is called the bottleneck. The name is, as we said, Tishby et al. Is it new to us? No, it is not. Look at this classical problem of remote source coding. Why whatever you see is not the source, but a noisy version of it? Why? You want to do remote source coding by definition. You see remotely, encode, compress the source. But the distortion is measured, general distortion, as we like to do in information theory. This distortion is measured logarithmically. Logarithmically means, in other words, that we wish to minimize the conditional entropy of x given this. So, because we have this, x is given, here we don't optimize. Minimizing that maximize the mutual formation. It's the same thing. And the remote source coding is not that new. Dobrushin, 62. Indeed, all examples he gave you was with the MMSC, but the results are general. If you want, okay, for general results, we have also not that new, not 62, but 75, the Witzenhausen-Wiener, which has everything, including the Euler-Lagrange equation that were used years later. Here it is, of the optimization in general. Is it all? No. What do we have here, Yossi? Common reconstruction. Hello, Yossi. What is common reconstruction, friends? Come on, Yossi. Common reconstruction, friends. Y, look at y as the source, not x. Look at y as the source. You want, what is common reconstruction? You that have the source, you want to know what gets reconstructed. And the receiver has also side information like Wiener's div, but it cannot use it because I need to see the picture, medical things and so on and so forth. So Yossi came up with an expression. Here is the expression. Again, this whatever we need is this, where the reconstruction is based only on you, only whatever gets transmitted. So minimizing this maximizes mutual information. Same thing. Same thing. Is that all? No. How about information combining? Why do we need information combining? A work by Sutskover at the time, the student of myself and Jacob Ziv, who also is here but could not come to the talk. He said the following, look, the input is y, you have two measurements. U and x, given y, they are independent. Why did we need that? At the time, belief propagation, LDPC, it was really crucial. What do we want to know? We know the specific capacities from u to y, from y to u, from y to x, and want to minimize and maximize this expression. Both measurements. Here it breaks down like this because of the Markovity. This, as we said, is given. For the bottleneck, it's C. This is given because y, x, and y are dictated, predictated. So, maximizing the relevance in their term means minimizing the information combining. Same thing. Just the very same thing. And here there is a beautiful tutorial on that by Landon Huber, not on the connection of information combining, standalone. Are we done? No. How about the S1R slot the corner problem? Classics over classics. X and Y are encoded at different rates. They're dependent, of course. And for a given rate Y, what is our X? So you can recover X losslessly. This is the result. Again, same thing as the bottleneck. Let me skip the connection. And here are the reference of this problem. And actually, because I knew I'll be in time constraint, this is not the whole picture. In a lot, but I'll focus only on that. Not the first part is not there. There are many others, like air keep cover investment. Investment. Same thing verbatim, if you look at it the right way. Investment. Nothing to do with communication. Okay, what can we say about Gaussians? Vectors, not scalars. Indeed, Chechik and Tishby here showed that the channel from Y to U should also be Gaussian here, and got the explicit results. The results are put in a way, in a nicer, same results, but in a nicer, more elegant form by the Swinkballer and Matz much after. Same result, but in a nicer, very readable, simple form. So for Gaussian, no big deal to show the bottleneck. What about CEO problem, as we mentioned, with log loss? It's exactly the same again. What do we want? We want to minimize the distortion measured by logarithmic loss, which is conditional entropy from here to here, where we have different encoders, not cooperating encoders, getting noisy version of that. So, and as we see, the general CEO problem for many users with MMSC is not solved. This one, because of the log distortion, is solved. It's solved for general, and again, the result, Quartet-Weissman, which I mentioned. As we said, the simple bottleneck problem is not enough for us, for our business, theorem. We need what is known distributed information bottleneck. You have many relays, many base stations. So distributed information bottleneck actually is more than was introduced, called by Tishby bottleneck, but in Witzenhausen we have indirect rate distortion problem really solved to the end from all aspects. But here we need many relays. Again, if you look at that in this work of Estela Zaidi last Zurich seminar, you'll see the result, the distributed bottleneck, very similar to what we have. Of course, under oblivious consent, there is not much difference. So here it is. And for the Gaussian thing, again, everything breaks down simply to log determinant, this or the other. Just to mention a special case, just to see some numerical examples. 2. CO with two encoders, or 2 relays if you want. X, very symmetric. Y and Y1 and Y2 are same SNR, independent noises, Gaussian, everything simple. X is also Gaussian. What do we have? The maximum mutual information from here to here. As we said, we can look at it joint decoding the compression, and one can come up with the formula, the exact formula. Here it is. Say, let's take some bounds just to get an impression. Say both relays cooperate, fully cooperate. then you have the standard bottleneck problem. Why? Whatever is received, it's two antennas of that signal X with different noises. What is the result? Immediate. They really sum their signal, that's the best thing to do, and you get the bottleneck result. Here it is. An upper bound, of course, because I let the relay cooperate. This is the THB formula. Let's go the other way. No joint compression, nothing. I compress the signal like a Gaussian codebook and a Gaussian source and so. What do I get? I get the same signal Y, but with additional noise, that's all, the compression noise. So let this one sum the signals with have some more additional noise. That's a lower bound, of course. Here it is. And here is the formula. So this example, we see the joint decompression decoding is not at all trivial, even for this simple case. So how do we said bottleneck? It's very nice that you use it for your own business, deep learning and so on. There is enough evidence that these measures of mutual information are relevant. I accept that and cannot argue with that. Okay, so how do we calculate it? Not all the word is Gaussian, enforcing X to be Gaussian. So there are very nice algorithms. Some are suggested by Stella Zaidi, but if you look deeply, and that was also their motivation, not that far from our well-known Blau-Tarimoto thing. So also here, formation theories practically have a lot what to say. Skip that. Okay, let us wrap up. Whatever we studied is the cloud radio access network, uplink, and under the oblivious, the nomadic approach, and the full thing, the full capacity, which is generalization of that work with Amichai here. And the oblivious processing is very, very appealing from the practical point of view. And actually, as we saw, DOF, degrees of freedom, lossless. You don't lose anything. Quite surprising. And as we see, also, even if not asymptotic, also here we have bounded rate loss with not oblivious techniques, and all connections to bottleneck. So, where are we to go? Very nice to discuss the uplink. How about the downlink? Quite a number of results. And there is a tutorial that with Simeone we publish in Signal Processing magazine that discusses that. There are also duality by you, Petir, and others, but not enough. It's way more to go here. Why duality? Why I speak about that? Downlink, uplink, different thing. Why? Because it equals infinity. What do we have about the uplink? The MIMO multiple access channel. The downlink, MIMO broadcast channel. Those are dual, as we know. Though the achievable schemes are very different. There's the paper here, joint detection. So maybe duality there is there also for finency. Duality, what aspects, what are the interpretation on the bottleneck thing? Now I said, very nice, optimal Gaussian inputs because log determinant, I want, take even the simple scalar bottleneck problem. X, Y is X plus noise, and Gaussian, and U. What is the power constraint input with power 1 that optimizes the mutual information? Gaussian? No way. Amichai can give the evidence. There is a counterexample in that work. No way. Conjecture? Discrete. Though we have only the average power constraint. Upper bounds. So far, Cutset upper bound. Really, we need something better than that. And there are ideas how to go. I'm working on that with Arfair Rodsger on these issues, quite involved. Because upper bound no obliviousness should apply for everything. Bounds on general information bottleneck problems. There are quite nice results by Painski, quite more recent, Painski and Tishby. And as we said, okay, let's look back at this bottleneck problem and do not assume everything C per channel use like we are used to. Say we want, now it's very, very timely to discuss scaling with the block length and so on. We have a block length of n, and given n, not necessarily large. And again, I want to maximize the relevance, the mutual information between x and u, under the constraint that y and u is smaller than 1 bit, no matter what n is. Not scaled with n, like 1 bit. Very difficult problem. This is the Courtait-Kumar open conjecture. And the conjecture says, okay, just transmit 1 bit, 1 channel output, forget the other. The other extreme, where we have n minus 1 bit, n is transmit everything. N minus 1 is solved. Is solved by whom? Vassim and Or, both of them are here. But limited thing. Very nice to discuss, very nice here to discuss the problem of discrete time as we did. But things are continuous time as we know. Here, what do? Filters and so on and so forth. The standard bottleneck problem actually in continuous time, which changes the water pouring theory, optimization very different, has been actually addressed quite recently. Homri, Mikhail Peleg here, who sits here, and myself. And there are quite a number of other problems that are very interesting. Let me conclude by the following. Complexity we measured by the mutual information between y and this u. C, that's complexity. Complexity in their terminology, for us is the frontal link. Complexity. How about measuring complexity by the entropy of u? That we considered with Mikhail. Why? We didn't want to have optimal source coding. You buy equipment, you buy Lempel-Ziv equipment that sits at home that should work for anything. Lempel-Ziv, compression, exactly, but better the entropy of the source be finite. So under this constraint, we managed to show, Mikhail and Homri and myself, that the function, the channel from y to u is deterministic. U is just a function of y, that's all. Under the entropy constraint. Okay, very nice for our, I gave you the motivation. And then, surprisingly, we see this paper that actually, for deep learning, this paper argues with Tishby. Said, no, look at our results with this entropy constraint. They are more realistic for our problems. It has nothing to do with the problems we are considering, than the mutual information constraint. So with that, I would like to stop. Here we have about theorem, only tutorials. Those are tutorials. The number of references are counted by the thousands. Thank you. Yes, Achim.
One thing you didn't touch upon is the energy for processing. And I think it's a very big asymmetry between the up and down channel, because if at least the receive processing, and the down channel is battery operated.
The energy of processing where? In the cloud or in the relay?
In the end.
In the end is what?
In the uplink, you process, I guess, mostly
At,
you have power.
at the cloud.
Right. So there it's just the cost of energy, heat, etc. When you talk about the down channel, which you didn't today, the processing, I understand,
At the
is mostly
users.
the handset. There it's battery operated, and that can kill you if it becomes extensive.
Yeah, but remember, let's look at the case of C equals infinity. Just a simple case. C equals infinity, what do we have? That means that the cloud controls all the antennas of the relays. It tells them exactly. This is exactly the MIMO broadcast channel. You are a user, and there is a MIMO broadcast channel. So whatever you have to use here is at best, something which is related to standards like dirty paper coding for the Gaussian model, which is not that complicated, especially not the simple version of that. Tomlinson, Harashima, and so on, really not complicated. And sometimes even not that. It's, kind of joint layer decoding, say, Gaussian scalar broadcast channel, which is degraded. You don't need the dirty paper. So there is no problem. And they also not with finite C. Why? With finite C, it's up to the cloud to think what to do best. So you can say, okay, because I transmit whatever the relay transmits is not whatever I give in it, finite rate, it's a noisy version of it. Okay, you have MIMO broadcast plus additional noise, then we are fine. But you can do much better. For example, one of the nicest results there is actually uses the fact that you want source encode when the noises in the reconstruction are correlated. That usually you don't want to do. This is called multivariate compression. The expression, what can you achieve, appears in the Cover El Gamal book. No, not Cover El Gamal, El Gamal Yezer, with Young and Kim book. And that is fundamental here. That is, by the way, this observation got us, as I mean, as well, COCO1, the signal processing joint paper award of this year. This observation. Yes, Ori.
Shlomo, so you mentioned discrete distributions as a possible good choice, right? The problem you discussed. So I was wondering if you took a uniform distribution over a PAM constellation, then you could actually get the structure in IID Gaussian, not Gaussian, in an IID codebook formulation. So maybe you could get the computing forward and your results in a sense on one line.
Yeah.
You can prove both.
In a way, I said discrete distributions are optimal, but if you look at least at whatever we try to do, the counterexample is for low SNR, Amichai. For low SNR, when Amichai has, just binary signals, plus minus one. For higher SNR, the issue is that for higher SNR, the points indeed diverge, and I'm not at all sure that the cardinality is finite. Actually, I'm sure that it's not.
So, but my question would be, let's say you take a finite cardinality,
Yeah.
you scale it with the SNR, just like you do, in
Yeah.
Gaussian channel using a PAM. You don't lose a lot with respect to Gaussian, right? By using a uniform PAM.
Yeah.
But then you can also gain the structure, right? In cases where computing forward is good, you would get it for free.
Yeah. You will definitely gain over the curves here, definitely.
Maybe you could just get something that takes both the computing forward and your scheme.
Maybe. Good idea. Maybe. Except, as we said, we had problem with computer forward for really high SNR because.
Yeah, but you don't have to do compute. You can also do compress with it.
No, but you cannot gain from anything of this kind for high SNR because, as we saw, oblivious, the very oblivious issue is optimal. With obliviousness, don't forget, oblivious, you say do oblivious, but with discrete alphabet.
Saying you're going to get everything automatically.
Should really be considered, but whatever we try to do, and we try to optimize over the alphabet, not just taking, uniform, it didn't give us, beyond that, very great things. So,
It's very difficult optimization.
no, but numeric, but that we did. Remember, Amichai? So it didn't give us something, to write home about. So I'm not that sure.
You'd just be very surprised that it loses anything.
No, loses it's not. It must beat the Gaussian. Must. The Gaussian input, it must beat. But the issue is that it didn't win that much. Must beat the Gaussian. The Gaussian is not optimal.
Maybe we should take further questions offline. Okay, so thank you very much.